This is the fourth section on the acidic environment, where we start to look at the main ideas behind acids and the development of the theories of the acids. And the specific people named are Lavoisier, Davies, Arrhenius, and Bronsted-Lowry, and the Bronsted-Lowry theory. And we're probably only going to get to touch on to the Bronsted-Lowry theory in this section of the work. So we'll be dealing with these first four out of this set of slides. Historically, we're starting off with Robert Boyle, who had done a lot of work on gas laws, but he also had provided us an operational definition of acids as things that have sour tastes, and alkalis are bitter, and acids are corrosive, and they change colour in vegetable dyes, which we know are indicators, and they react to neutralise each other. Now, this is an operational definition. It doesn't really explain anything that's going on. So the first one to actually start to try and explain anything that's going on is Lavoisier. Now, remember, Priestley had previously discovered oxygen, and Lavoisier had used the oxygen to react with non-metals and found that they were acidic when they were dissolved in water. So he said the acidity was due to the oxygen. But of course, not all oxides are acidic. Some are basic, some are neutral, some are amphoteric, and not all acidic substances even contain oxygen, which is something that was discovered later by Davy. So Humphrey Davy had already been working on looking at extracting metals from their salts by using electrolysis, and the metals he'd been looking at were like sodium and potassium, the group 1 metals. And around about the same time, you've got Priestley, who had actually made hydrogen chloride gas, which is not hydrochloric acid till you put it in the water, by reacting sodium chloride with sulfuric acid. So with these two ideas, you had Davy putting the two ideas together, and he dissolved the acids in water and then used the solutions in electrolysis and saw what gases were produced. And when you had hydrogen chloride gas in water, it becomes hydrochloric acid, and only hydrogen gas and chlorine gas were produced, no oxygen. So the acidic nature can't have been due to oxygen and was therefore due to hydrogen. So that sounded really good, except that there are many hydrogens that are nothing to do with being acidic, things like methane. So von Liebig extended his idea when he said that there were replaceable hydrogens that metals could react with, but he didn't really explain why some hydrogens were replaceable and others were not. Cervantes Arrhenius had already been working on electrolysis and the need for an electrolyte for there to be solutions to conduct electricity. You had to have ions in there. So his experiment was to use electrolysis of acids. And the one thing that all acids produced when you had electrolysis was hydrogen gas. And his suggestion was that there must have been H plus ions because it was an electrolyte, conducted an electric current. So there must have been H plus ions that interacted with the electric current to produce hydrogen gas. And that all acids produced that because all acids produced H plus when they were put into water, when they dissolved. So he developed the pH scale, and he also said that all bases produced OH minus when they were in solution. And his idea of neutralization is pretty much the one we work on, and that is an H plus ion reacting with an OH minus ion to form water. And we still use this, but we've kind of extended the ideas even further now. But one of the problems was it didn't deal with metal oxides that couldn't dissolve, or carbonates, they're not explained, and that not all salts are neutral, and it didn't deal with reversible reactions, which was its biggest failing. So at the same time, two scientists that were not working together at all came up to the same conclusion, and that was that it somehow there was an interaction between the acid to the base and the solvent, which was water. And that in the process, H pluses, which are protons, were being donated between one species and another. So if something was donating a proton, something else had to accept it. So it's a bit like when we had the electron transfer reactions. If something gave up an electron, something else had to accept it. So that within the same reaction, you would have a species that's giving up a proton and one that's accepting it. And notice how this one still produces OH minus in solution, so it still fits the Arrhenius definition. In the same way as this one does with the hydrogen chloride gas going into the water. The hydrogen here is being donated onto here, and that makes that the hydronium ion and the chloride ion, and that's the proton donor, and that's the proton acceptor. So all of this, there's still H pluses and OH minuses in these solutions, but it allows for reactions where there's no OH minus involved at all. There's only a transfer of protons. It did allow for the solvent to be involved, and it allowed for the reversible reaction. And that's really important. The self-ionization of water we have come across before, but you can view that as one of them donating a proton, one of them accepting a proton. And so this one donating a proton is an acid, and that one accepting it is a base. And of course, that's a reversible reaction with a very, very small amount of this actually happening. If you consider the reaction down here with hydrogen fluoride and water, it's going to form the H3O plus ion and the F minus ion as well. But if you consider just the fluorine, or the fluoride rather, you've got the fluoride with the hydrogen behaving as an acid going that way, and the fluoride ion without the hydrogen taking a hydrogen and becoming the molecule going back the other way. It's behaving as a base. So you've got the one species, really, the fluorine, or the fluoride rather, with the hydrogen and without it as the acid-base pair. It's one thing that with the protons and without the proton. And that's the acid and its conjugate base. So here's a list of all these acids and their conjugate bases that go with them. And you'll notice that all of these have got the hydrogen on them, and that the other one, the conjugate base, is the same thing written without one of the hydrogens. Similarly, all these bases have conjugate acids, and here they've got the without a hydrogen, and here they've got an extra hydrogen. So because this one and this one are an acid-base pair, that water there is, and the hydronium ion are an acid-base pair. So the hydrogen fluoride and the fluoride ion are a conjugate acid, one conjugate acid-base pair, and the water and the hydronium ion are the other conjugate acid-base pair. And within a reaction, that one will be the acid, that one will be the base. This will be a conjugate acid of that base. This will be the conjugate base of that acid. And you need to be able to identify those. We'll be going on with more about those later on, and that's another syllabus dot point. So there is a relationship between an acid and its conjugate base, and that these occur in pairs. So that's the next section, was we will be going on to deal with that.